Okay, so let us talk about lexical resources. So recall one of the slides from the first lecture number 1. There we said that one major challenge that makes natural language difficult for automatic processing is ambiguity. Ambiguity means that one and the same thing may have different interpretations, such as in terms of meaning, the word bank may have different interpretations, which we call polysemy. So it has different meanings, which are sometimes related with each other, right? Yeah, so this is the definition of policy, that a thing has different meanings, but which may still be related with each other. And then we have other forms of ambiguity that relate to spelling, pronunciation, and syntactic parsing, for example. One particular case of ambiguity is an even more severe form compared to polysemy, because polysemy means that the different meanings that a word can have are related to each other, but in terms of homonyms, the different meanings that a word has are not related anymore to each other. A particular case is the word saw, or like one instance of that is the word saw. Another instance would be the word can. In both of these cases, the word has different meanings. So the word saw means, on the one hand, it's a past tense of the word see. On the other hand, it's a singular form of the word saw, which is a tool to to do some manual work and cutting wood into parts, for example. And those meanings are not related, at least not in contemporaneous English. So maybe historically they were related. I do not know this, but at the moment in modern English they are not related. So this is the main challenge. And how can lexical resources help us with dealing with such challenges? Let's see how they can. But before we see this, let's start out with a definition of a lexicon or / lexical resource. So by a lexicon, we understand a collection of words or phrases, or maybe sentences, but typically not sentences. It would typically be words or phrases. And in most cases, we have associated with this some extra information, such as a lexical category or some definition / explanation. So we have words or phrases together with something else, which could be a categorization or a definition. And those words in a lexical resource are called lexical entries. And we see an example here where we have a lexicon, and our lexicon would have 2 entries. Let's say that could be in a book, or it could also be in computerized form, where it says saw, and maybe we have an indication that differentiates the different meanings of the word saw. So we would have saw 1 and saw 2. Then we have this extra information, which in this case could be that saw is a verb, and in this case saw is a noun. And then another definition or explanation string, such as this saw here is the past tense of see, and this saw here means a cutting instrument, right? And this thing here is the part of speech or lexical category. Good. Now we can also have word lists that do not have those extra information. So they only consist of words. So and one such example use case is the Unix dictionary. So if you on Unix go to user share dict, this is a directory. If you go in this directory, you will see different word lists, and we can see this right away. Let's make a brief illustration. So now we go to Unix, we do a little bit coding. So I'm already logged in. Now I am in the Python interpreter. Now let me log out. So we go to user, we go to user share dict. Just a second, user share dict. So then we do an ls on this, and you see here are the word lists. So we have this word list here. We check how many entries there are. There are 99,000 words in the word list. and we can look how they look like. So here are all those words. So you see it starts out with capital A, capital B, capital C, and I think if we go to the end, so if you go to the end, then we also see lowercase words. So here you see like even like in French writing. Okay, and you also find in the same directory, you see like a word list with American spelling and a word list with British spelling and other word lists. So Unix has this, and there are other word lists that you can consult. Also ones on the internet, for example. Yes. So now the good question is, what are we going to use those word lists for? What can we do with those word lists? So there are multiple use cases that you can think of. First of all, we could have a word list, let's say, that covers 100 to 1,000 words, that covers a specific domain terminology, such as biological terms, computer science terms, philosophy terms. So that could be interesting if we research a big corpus such as the World Wide Web or Wikipedia pages. So we could say, if we are biologists, we are mainly only interested in biological Wikipedia pages. So we keep all the Wikipedia pages that contain at least at least 1, 2, or 3 biological terms, right? So that could be a use case. We could also define a basic vocabulary with those word lists. For example, imagine that we want to do train an algorithm, so like a NLP algorithm that is doing some task. Now, if we train our algorithm on the World Wide Web, so there's really a lot of so there's text in different languages. So if we take all of those, if we construct a vocabulary from the World Wide Web, so this will really have dozens of millions and millions of entries, because we get words in different languages, we get numerical strings, we got all kind of things. So this will really be a heavy load for our algorithm in terms of memory and in terms of efficiency of processing. So we could just say we're only interested in the basic vocabulary. So we learn statistics only for the basic English vocabulary, consisting of 10,000 words, and we're not dealing with other words, right? So that's what we could tell our algorithm to make it more efficient. We could also have a list of place names, cities, countries, regions, where we have a word list that only contains countries, right? And then we could do the same for the domain terminology. We could, for example, only extract sentences from Wikipedia that are in certain countries, let's say Germany and the US, so that maybe if we're interested in the relationship between Germany and the US. We can also use the word list for spell checking, and that's what the Unix word lists have originally been designed for. So imagine you want to you define a word list that contains the basic English vocabulary, let's say of 100,000 words, and you then go on Twitter and you check somebody's spelling, or you check your own spelling when you type something. You can, if your word is not in the word list, then there's maybe a good chance that you have just misspelled. Of course, it's also always possible that you have used a word that is just not in the word list, but if the word list is 100,000 long and contains the most frequent English word, there's a good chance that you have made a spelling mistake. And we can check in the word list, like from Unix, which is the nearest word, and maybe we suggest you to replace your potentially misspelled word with this nearest word. We can also define a word list that contains only stop words. So stop words are high frequency words like to, the, and also. Such words exist in all languages. They are also called function words. But okay, more specific function words. So a function word is everything that's not a content word. So a proposition is also a function word. And such words, they make up a huge fraction of all texts. So one says that function words make up about 50% of all texts. but they contribute very little content. They contribute very little meaning. So doesn't matter whether you talk about politics or whether you talk about sports, you will use the same function words, and they contribute nothing to distinguishing those two domains, that is politics and sports. So often we want to get rid of function words, and in particular of those high frequency function words like to, the, and also, and a couple of others, of course. So we just remove them from our text because they contribute nothing to understanding the text, at least potentially from a computerized perspective. So we better remove them so that our algorithms can work more efficiently. So these are some use cases of word lists. Where can we get word lists from? So we've seen the Unix word list, and there are other word lists in NLTK listed here. I will not go in detail into them. So there's like CMU Dict, which is a Carnegie Mellon pronunciation dictionary, stop words lists in different languages, VerbNet. This is a corpus that relates verbs, but we can also just get a word list from that corpus. We can also use from NLTK the corpus words, which is basically just a word list. So, and to illustrate you how to use that, how to do this, let's again go back to the code, and let's try it out a little bit. Okay, so we go to Python, we import NLTK. Then what we do next is, let me check quickly. So we go to NLTK corpus, and we go to words, and we can, we can get all of the words, you see, that are there, and these are quite a few. So we just type in how many there are. There are about 230,000 words, and then we can store them in a variable and use them for any of those purposes that I have just outlined. But before doing so, let's just have a look at the top 10 words. So this is like the, you see that they are apparently stored in lexical ordering. So they are sorted in lexical ordering. We can also, let's see if there is CMU Dict. So we check what is there. So there are a couple. You see prop bang, that was also in our list. CMU Dict is also there. Okay, NLTK corpus CMU Dict. That's what we're gonna type, and then we're checking the words. And the other one was 230,000, and this is half of it about, right? So again, let's check the top 10 words. Okay, also seems to be sorted in alphabetic ordering, except that it seems to be all lowercase. And the important thing is that we're kind of misusing CMU Dict now, because it was originally not designed to be a word list. But let's see what we can actually do with the CMU Dict. Let us check whether we can, like there's this dict variable. And let's check what we can, or let's check entries. Okay, so we're gonna, so what you see here, so here you see these are the entries, and they should be the same as the word list. So this was 133,000, right? So it's the same again, and I check here the 100th entry in the CMU Dict, And what you see it is doing here, it's the word abdication, and it's actually giving the pronunciation of the word. So this is abdication, and you see here is like the TI that is pronounced in English like sh, and you see that here is the corresponding pronunciation sh. So semiotic is actually a mapping between words and pronunciation, but we can take all the words and get a word list from that. Okay, so we can get word lists from those corpora listed in NLTK corpus. Let's do some applications that we can do with, let's do some further applications that we can use word lists for. So one application could be to get unusual words. So let's say that we have our text, and what we do is we go over all the words in our text and we check whether our word is alpha. So what does it mean is alpha? It means whether it's alphanumeric. So basically whether this is a proper word, right? Let's again go to let's go to Python again. So we're gonna check. So let's say we have a string like cat, so we can check is alpha, and we go to dog, and then we print this, and it says returns true if all the characters in the string are alphabetic. So if it contains a number, it's not alphabetic. So let's check ABC is alpha. This is true. ABC1 is alpha. This is false. Okay, so this is also a nice nice to have functionality. So we check whether this is really a proper word. So we go over all of our words in the text. We check whether they are alphabetic words, and we lowercase the words. Okay, let's just say for the sake of simplicity, we're only gonna we don't distinguish between lower and uppercase, which is a reasonable assumption in English, because English doesn't have much lower and uppercase, so it really doesn't matter whether the words are written lower and uppercase usually. But for other languages, it really makes a distinction. So for German, uppercase letters indicate nouns, right? So, and then we're not gonna deal with duplicated entries. So we're not gonna take the list of all words, but we reduce the list to a set. So if a word occurs multiple times, we only count it once. So this is what we're doing. So this is the vocabulary of our novel text, and then we compare this to the standard English vocabulary, where we do the same. We go over all the words in our NLTK corpus words, and we know already that the words there are alphabetic words, so we don't have to take this if condition in. And then we also take this to be a set, so we have two sets, and then we take the set difference between those two sets, and we take our text vocabulary, we subtract from this the English standard vocabulary, and we get the unusual vocabulary. So we get the vocabulary that is mostly in our novel text corpus, and then we return this in alphabetically sorted manner. And what we could do, for example, is we take NLTK corpus chat words. So we take the words that occur in chat but are not in the standard, like in a prototypical English vocabulary, and we're gonna see such entries here. So the A repeated multiple times, you see misspellings here, you see some, I don't know, this is like some some computer science terminology word, I would say, and that's what you're gonna see in web chat, for example, and you see that you can use Wordlist to find unusual words in your specific domain. We can also remove stop words, as I've said before. So here, first of all, we're gonna have a look at what are the stop words for English. How do they look like? So this is a, about, above, after, again, against, all, am, and any, are, as, and a couple more. Let's check how many more by going again to the Python shell. Let's check how many more there are. NLTK Corpus stop words for English. So it's not too many, as you can see, right? It's like about 50 or so. Oh, okay, a little more, 180. We can also check for German. There are a couple more. So these are function words, as I've said before, high frequency function words that usually have little semantic content. So they really oftentimes contribute not so much to the meaning of a text, right? So these are our function words. Now what we're gonna do is we count how many non-stop words are in the Reuters corpus. Let's see the Python code that we're gonna use for that. We're gonna take our stop words for English, then we're gonna take our Reuters corpus, take the words from the Reuters corpus, lowercase them again, because again in English case is not so critical, and if the words are not in the stop word list, we keep them. Then we count how many words are remaining, and we divide by the total amount of words, and we see that 65% of the words are content words in the Reuters corpus, or 66%. So about 2/3 are content words, and the remainder is function words, right? Or is like those stop words, right? So those stop words, they take a huge fraction of the actual text, in this case 1/3, but they contribute not so much to the understanding and the meaning of the text. So we can get rid of 1/3 of the vocabulary if necessary from a computational perspective. Okay, to have a little bit fun with word lists, let's do a little bit of Python implementation with NLTK, where we choose where we do a word puzzle and choose words from a word list that satisfy certain criteria. And the criteria we can list as our mood happens to be, right? So let's say our mood happens to be that we want to have 6-letter words, words that have 6 letters or more, and they should contain those 8 characters on the right here. So they should only contain characters from those characters on the right here, no other characters. They should always have an R, and we can add further constraint as we are happy. So for example, we could say we want to have at least one 9-letter word, we want to have no foreign words, no proper names, no plurals and endings, no plurals that end in S. These are constraints that we can add, but let's just consider now a subset of all the constraints that we've listed here. So first what we do is we import NLTK, we make our letters here. So those 8 letters, 1 letter appears twice, the V, and we make a frequency distribution. In the previous lecture, we've seen this conditional frequency distribution. Now we see a standard frequency distribution without any extra condition. So what is this basically? What we're getting here in the variable is sort of a hash where we store the frequency of all the letters. So E appears once, G appears once, I appears once, V appears twice, R appears once, etc. So this is our frequency distribution. Let's look at this in terms of our Python shell. So we type this here, puzzle letters. So I've already done this for you, and you see here's the frequency distribution. All right, it's like a hash that gives the frequencies of each of the characters. Now what we do next is we say this is our obligatory letter R. We make the we get our word list, so we just take the NLTK word list, and now we type our code, and our code is like this. So we go over all the letters. We go over all the words in our word list. We say, okay, let's take the first condition here. The word should have 6 letters, so it has 6 letters here. It should have the obligatory string, so the center letter, that's R, so the obligatory string must be in there. And we further require that the frequency distribution of our word from our word list should be less than or equal to the frequency distribution in our letters. So what does this mean? So the frequency distribution of the string here says E appears once, G appears once, I appears once, V appears twice. So we can have 0, 1 E's, 0, 1 G's, 0, 1 I's, 0, 1 or 2 V's. So this is the thing, right? For each character, we can have at most this distribution that's given in puzzle letters, right? And then we print the words. And let's check, like Clover satisfies this. So it has 1 G, it has 1 L, it has 1 O, it has 1 V, it has 1 E, it has 1 R. It has no other letters, right? It cannot have like a D or something, like D like doctor, right? It cannot have a D because that's what our constraint says. The frequency distribution should be less than or equal to letters. Okay, and we can actually go check this out here in the Python script. Let's check. So this is the code. Now we check how many words did we find. We found 19 words, and they are given here. So now you can continue to play around with this, and you might wonder what happens when instead you say puzzle letters. So this is the frequency distribution of our 9 letters, should be less or equal than the frequency distribution of the word. So which words are we getting out there from our word list? So we get 7 words. And what does it actually mean to go in this way? So we say the frequency distribution of W should be greater or equal to puzzle letters. So we should have 2 or more V's. We should have 1 E. We should have 1 G. We should have 1 N. We should have 1 L, 1 N. That's the N. That's the L. 1 E. And we can have arbitrary other letters such as C, twice even here, such as such as other ones. A is also here, right? Which is not given in the original letter. So and one interesting thing is, because I played around with this, this is very fancy. If you do the equality sign the other way around, so you could say A is less than or equal B, or you can say at the same time B is greater or equal A, which means the same things in terms of mathematics. However, It's not the same thing in terms of NLTK. So here we have puzzle letters less or equal than frequency distribution, which is the same thing as frequency distribution greater or equal than puzzle words mathematically, right? So now we drop this here. So this would actually be mathematically puzzle letters. That would be mathematically equivalent. But we see that the result is very different. So all of a sudden we have 100,000 hits, and I wonder why this is the case. And the answer is actually that they implemented it slightly weirdly in NLTK. Let me just show you this quickly. So somebody has already been asking this, why the comparison is not symmetric. So if you say A greater B is not the same as B smaller A, so why is this the case? And it turns out like this is implementation, you could call it bug or implementation problem of NLTK. So just be sure how you type the equality in this example. And other than that, this has been a nice application of selecting words in a word list that satisfy arbitrary conditions that we may come up with to find interesting words in the English language or in the Chinese language or in the German language. And you can continue to find other conditions to get even fancier words. So what about word lists in different languages? Let us look at the so-called Swadesh word lists, which are also available in NLTK. So these lists go back to the linguist Maurice Swadesh, who had the theory that like languages all have names for similar concepts. So he thought that there are some basic concepts in different languages, and those basic concepts are like mother, father, daughter, meat, etc., etc. There are about 200 common concepts, and he claimed that all the languages have words for those concepts. And then what he further claimed is when we look at the words for those common concepts, we can measure the similarity between languages. So this is not what we're going into now, but this is the basic historical linguistic background. So this guy is has been a historical linguist, and he wanted to infer language relationships. So for example, that English and German have a common ancestor, let's say Latin, and he wanted to infer such language relationships by looking at the words for those common concepts. And we, for our purposes in this course, we can use those Swadesh lists. So now we have the Swadesh corpus. We can see the languages which are covered. So in this case, seems that there are only like a handful of languages. In reality, like the full Swadesh list that you would find on the internet, and which are oftentimes compiled by crowd workers. So like by people with some linguistic background, but let's say they are not necessarily full expert for these languages. They compile those Swadesh lists for different languages. But NLTK has only a handful of languages apparently. We can then check the words that are in the English Swadesh list, and you see that the words are I, you, thou, he, we, you. So these are some like pronouns, but they're also function words like big, long, wide, and they refer to the, as I said, they refer to the elementary concepts that apparently are shared across different language communities. So what we can do with the Swadesh list, because they exist in multiple languages in NLTK, we can use them as a dictionary, right? So let's say we want to translate from German to English, then we go into the Swadesh list for German and English, and we store this in a variable de2en. We list up the variable, and you see that here are the words for the common concepts, right? So ich corresponds to I, du, sie corresponds to you and thou in English, for example. Okay, and then we can even make a translation dictionary out of this DE to EN, and we get, at least for about 200 words, we get translations in the handful of languages stored in the NLTK Swadesh list. And we can, of course, as I've said, we can do this across multiple languages. So let's say we want to compare the Germanic languages to the Romance languages. So Germanic is English and German, and Dutch, NL is Dutch, to the Romance languages, French and Latin. So then we go over some concepts that we're interested in, like the concepts could be concept number 139, 140, 41, 42, and we print the entries, so we print the words that our languages have for that specific concept. So it would be say, sagen, segen, dir, dicere. And as you can already see, as I've indicated previously, you can infer maybe from those translations that some words are more similar, some languages are more similar to specific other languages, right? So we would, for example, say dir and dicere. So these are really like intuitively similar, right? And also say, sagen, segen is also intuitively quite similar. The same here is with singen, sing, singen, singen. These three are quite similar strings. Chante and canare also, right? And indeed, so these Swadesh lists have been frequently used to infer those language relationships and are still being in use today. As I said, if you look up on the internet, you'll find Swadesh lists for many more languages than the handful of languages given in NLTK. Those 200 concepts are also have been criticized over the years, so this is quite old concept. Swadesh is from the 50s, 60s, 70s of the 20th century, so this is like 60, 70 years old. So the number of 200 concepts has been criticized. I know of lists that exist nowadays that have up to 1,000 concepts, and whether this method of like comparing languages and dating languages, so saying which language is an ancestor of which other languages, if this is really an accurate method is also up to discussion in the scientific community. But at least for our purposes, we now see that we have word lists across different languages, and interestingly and importantly, the word lists are what NLP people say aligned. So you have words for one and the same context concept, so that you can use those words for the same context to infer translations between languages, which of course then you could ultimately use in natural language processing, for example, to do machine translation, right? So this is one of the end goals of machine translation, to translate between the different languages.